Good morning. Welcome you to this session of thermodynamics. Today I will start the thermodynamics of multi-component system. So before this, while discussing the thermodynamics of reactive systems, we have recognized some part of thermodynamics of multi-component systems through the use of certain concepts and formulas. This is because a reaction involved number of species, a number of components, as we have seen that in the reactants there are more than one, usually more than one component. Similarly, in the products there are more than one component. So we recognize some of the rules or information on thermodynamics of multi-component systems. But today we will start again the thermodynamics of multi-component system. Rather, we will discuss it in details. So thermodynamics of multi-component system. So let us write multi-component system. Multi-component system. Now, at the outset, let us recall one thing, that while we first discussed about the state variables, that means for a system at equilibrium, the properties are fixed, and we require certain minimum number of properties as the independent variables or independent properties, so that if they are fixed, other properties are fixed. And this number of independent variables or independent properties to fix the equilibrium state of a system depends upon the number of components and the number of phases of the system. And this is given by a formula known as Gibbs phase rule, which we discussed earlier, but without the proof. The rule is like this. If I write that Gibbs phase rule, if you remember Gibbs phase rule, which gives the number of independent variables or properties to fix the equilibrium state of a system, this is like this F, this is the number of independent properties. F is equal to number of components of a system, number of components minus number of phases plus 2. Let us denote the number of components as R here, number of phases as phi. R is the number of components, number of phases phi, and this F determines the number of independent intensive properties that is required, that are required to fix the equilibrium state of the system. Okay, number of independent intensive properties. Now let us take an example, simple case which we discussed, which we have discussed so far, that if this is a single component system, that means R is equal to 1. That is single component system. Single component system, R is equal to 1, and a single phase system, phi is equal to 1. Single component and single phase system. Single component system and single phase system, what we get, F is equal to 2. That means there are minimum two properties are required, and they are sufficient. That means two properties are required to fix the equilibrium state of a system. All other properties are automatically fixed. So therefore, this comes from the Gibbs phase rule for a single component, single phase system. But if number of components are there, more than one, the more than one components are there and more than one phases are there, therefore the number of independent properties are more according to this Gibbs phase rule. The number of minimum number of or number of independent intensive properties are more. So for example, if we consider single phase, a system, single phase system with R components, then F is equal to R minus 1, just an example I am giving, R plus 1. That means for a single phase system consisting of R components, number of independent intensive properties required to fix the equilibrium state of the system is equal to R plus 1. So this way, from the Gibbs phase rule, we can find out the number of independent intensive properties to fix the state of the system. Now in this way, if I start like this, let us consider an extensive property. Now the intensive properties are those which are not dependent on mass. So, there are large number of extensive properties as we know whose specific values, that is the extensive properties per unit, must become an intensive properties. For example, specific internal energy, specific enthalpy, internal energy, enthalpy, Helmholtz function, Gibbs function, volume, they are the extensive properties. Similarly, the specific internal energy, specific volume, specific enthalpy, well, specific Helmholtz function, specific Gibbs function, they are the intensive properties. Now, let us start with such an extensive properties. For example, U, the total internal energy, which should be a function of any two other properties for a single phase system, single phase, single component, single phase system. Let they are expressed as a function of S and V. This is for a single component system, single component, single phase system, single component, single phase system. Now, first I will not consider multi-phase system. So, single phase I will consider multi-component. Let us consider the single component system where the extensive property U, the energy, total energy, is a function of S and V. Two independent properties are required and we choose S and V are the two independent properties to express the function internal energy. Where this S is the total entropy, this is also an extensive property, V is the total volume, it is also an extensive property. Now, if we consider a system consisting of R components and each components have number of moles N1, N2, N3 like Nr. That means the system having R components, and system is an open system which allows the material flux, that means material can flow out and flow in, which means, and this is valid for all the components, which means that this number of moles N1, N2, N3, Nr may vary as the system interacts with the surroundings. That means there is a change in the number of moles because of the material influx and efflux, okay, of the different constituents or different components. So, therefore, we consider a system of R components. So, in that case we can write this U, which can be written as a function of S, V and all other number of moles. That means the composition of the constituents. That means the R number of components are there and it depends upon the number of moles of the R constituents. Now, if you see this is an extensive property. If you write an intensive property for this system, that means if you divided it by the number of moles, that means if you just U by sigma n, then you see U as a function of S, V, and N1 by sigma n I denote as x1, this is the mole fractions, okay. X3, I just check the Gibbs phase rule first. Now, x1 is N1 by sigma n. Well, x2 is N2 by sigma n, like this. Now, here you see these mole fractions also satisfies the equation x2 plus x1, x2, x3 plus xr is 1. So, therefore, this is one constraining equation. That means, out of these R quantities in terms of mole fractions, they are not all independent. There are only R minus 1 independent quantities. Plus these two independent quantities, that means finally R plus 1 number of independent quantities, which is telling with the Gibbs phase rule that for R number of components in a single phase, the intensive property, that means U, which is a function of R plus 1. That means if R plus 1, that means it can be expressed in terms of R plus 1 number of intensive properties. That means we require only R plus 1 number of intensive properties. That means, of course, this will be small s, this will be small v, sorry, this will be small s. That means we require R plus 1 number of intensive properties to fix any properties. That means any of the properties, intensive properties, can be expressed as a function of R plus 1 number of intensive properties, which are the independent parameters or independent variables. So, this is in compatibility with the Gibbs phase rule. Now, I start with this, the U is a function of entropy, volume and N1, N2. That means this is the big U, that is the total internal energy, total entropy, total volume, nr. Okay. So, in a single component system u is a function of SV, but in a multi-component system of r components consisting of r components, as already we have told that this is a system, that is the r components, we have n1, n2, n3, nr the respective number of moles for the components. We can write that u as a function of SV and the number of moles. Now, if we make the differential, total differential, that means a change in u, a small change in u can be written in terms of this as del u del s at constant v n ds. This is simply an expansion in the differential form del u del v. Taylor series expansion, neglecting the higher order term, this is the elementary mathematics, s n dv. U is a function of s n. If it could have been a function of s v, then it could have been sufficient and n was not there. But now what happens, there are r number of n's. So, therefore, there will be terms like this del u del n I, where I is any ith constituents, sigma, this is at constant s, constant v and constant number of moles n j, where j not is equal to I. Well, this is for this dni, and this is valid, and this has to be done for all the constituents. So, this is sum of this I is equal to 1 to 1. So, you see an additional term, that is del u del ni dni at constant s, constant v and constant number of moles except this one. That means, when we take a differential with respect to the number of moles of the ith constituent or ith component, then all other components remain, the composition of all other components remain the same. All right. So, we can write this equation. At the same time, we know that for a single component system, du is del u del s at v ds for a single component, where n is constant. That means, these two terms del u del v at s dv. If we compare this equation with the property relations, we know the property relation du is TdS minus PdV. These property relations we know. For a pure substance, this is the property relation, du is TdS minus PdV. Now, you see, if you compare this equation with this one or the first two terms of this one, the first two terms is similar to these terms as a single for a single component system, because here n remains constant. When n remains, all n's remains constant, means it behaves as a single component system of a homogeneous composition. So, therefore, we can write the first term, that means this or this, that means as t, and this term as minus v. That means, we can write del u del s, okay, at constant v n at t, and similarly we can write del u del v at s and n is minus p. So, I can substitute this and I can write du is equal to, therefore, I can write TdS minus PdV plus del u del ni, the same terms dni, and this partial differential is at constant s, v and the composition of all components except with which it is differentiated. That means nj, j not is equal to I. So, therefore, we see for a single component system, this is the property relations, that if we have a multi-component system, the same property relations can be written with an additional term here in the right hand side, that TdS minus PdV. When the compositions do not change at all in a multi-component system, it behaves like a single component system, and these terms are 0, all the terms are 0. This is sigma I is equal to 1 to r, and then simply du become TdS minus PdV. All right. Now, let us find a similar relation if we start with H, the enthalpy of the same multi-component system comprising R constituents, as a function of S, not T, I am sorry, S, P and number of moles. So, the implications of this will be clear afterwards from the concept that why we are expressing U as a function of S and V and the number of moles, why we are expressing H as a function of S and P. In fact, this U always in internal energy, this is by definition, but we express it in terms of entropy and volume. That is because I will explain this afterwards, that in a closed, we consider a system where volume remains constant, or we consider that volume remains constant means that volume remains constant, then we can tell that this change in the U is an indication of certain energy potential. That I will come afterwards. Of course, here in volume is not constant, but there is a concept for which U is expressed in terms of S and V and H is expressed in terms of S and P. Let us first follow now in a routine manner as if we can do it, because mathematics, by mathematics we can express this in terms of any two properties. H could have been also expressed in terms of S and P, but let us express in terms of S and P and follow in a routine manner what happens next. dH is equal to, similar way I can write del H del S at P and N ds plus del H del P here, because P is the variable, is the pressure at constant S and N dP, plus similar way the summation of all the differentials with respect to this number of moles del H del N I, okay, and where S, P and N J, that means the number of moles of all the constituents except the constituents with whose moles it is differentiated, that means J naught is equal to I, okay, dNi, and this is summed up I1 to R. Again, for a single component system, for a single component system we stop here, these are the two terms. Again we can write dH, property relations, from property relations you know TdS, what is dH? du plus PdB plus VdP, and du plus PdB is TdS, so plus VdP. You can recall it like this always, you do not have to remember always the property relation, you have to remember the definition of H is U plus PV. So therefore it comes automatically du plus PdV plus VdP, and only this thing you have to remember, only one property relation if you remember, then it will be all right, du plus PdV is TdS. So therefore, so this property relation tells that if H is expressed in terms of S and P, therefore this T is del H del S at P and N, and V is del H del P at S and N. N means N is constant, but a single component system the N does not come because the one component and N remains constant. So therefore in a multi-component system if all N's are held constant, then this part is 0, it behaves as a single component system. So we can replace this as T and this as V, alright. So I can write therefore dH is TdS plus VdP plus I is equal to 1 to R del H del N I S P N J, J naught is equal to I dNi, alright. So this is another important equation. Now again in the similar way I now go for Helmholtz function F. Now if you remember the Helmholtz function which was discussed earlier, Helmholtz function, how it was defined? F is equal to U minus Ts. Now Helmholtz function, if that is one extensive property of the system, and if I express this as a function of Tv, let us consider Tv are the variables. So implication of these two particular properties Tv will be made clear afterwards, and the number of moles of the R components constituting the system, then we can follow in the similar manner, similar routine manner, dF is del F del T at constant V n dt, well, plus del F del V at constant T n dV plus again the same thing, the sum of del F del Ni, that means the mole of the ith component, and it is for T, V and Nj, J naught is equal to I dNi, and this summation is for all the components 1 to R. Again from this relationship we can express the differential df in terms of dt and dv. How? Let us see here. Now if we differentiate df, you differentiate this du minus tds minus s dt. Now tds is du plus pdv, so then du cancels, plus pdv, so minus sign, so it will be minus, first I write this thing s dt minus pdv, minus s dt minus pdv, alright. So therefore we see that we can express f in terms of dt and dv. This is for a single component system, and which is similar to this, that means for a single component system we have to express this df is minus s dt minus pdv. We will stop here for a multi-component system if ni there is no variation in all the moles of the constituting components. But here it is not so, so therefore we will substitute S as this and P as this minus P as this as we did earlier, and we get the same type of thing STD minus PDV plus the additional term. So always we see the additional term comes del F del Ni dNi, and this partial derivative dV Nj, where j naught is equal to I, and this summation is from I is equal to 1 to R. Alright. Similarly, I can derive another extensive properties. There are 4 very important extensive properties, that is already we have covered U, internal energy, we have covered enthalpy H, U, we have covered enthalpy, then Helmholtz function. Now we will come to G, Gibbs function, G, Gibbs function, Gibbs function. Now we will go to Gibbs function. This we have done, this we have done, Helmholtz. Now Gibbs function, or Gibbs function, how it is defined? This property was defined as H minus Ts, if you remember. Okay. So now if I express again, there is an implication of it that G as a function of T and P, F was done T and V, then F was expressed as a function of T and V. Here it is T and P and N1, N2. I think these implications you can appreciate while we discussed exergy. We have seen that what is the implication of G. When temperature and pressure remains constant, it is the change in the Gibbs function which gives the availability or the maximum useful work if the temperature and pressure is same as that of the surrounding when a system interacts with the surrounding. Okay. So now if I write this in the similar fashion, I can write del G del T. This is again a routine matter, P n dt plus del G del P at T n dP, well, plus again we get the same thing del G del N I dN I, where T, P and Nj, J naught is equal to I are held constant, and this summation is taken from I is equal to 1 to R. Now we see that we have got the 4 equations one by one. If we see that U is this one, du, we get this equation. Then for H, we got these equations. For F, we got this equation. Okay. And for lastly, for G, we have got this equation. Now let me write all these 4 equations in a single, the same place. let me write this thing in the same place for a better understanding. That let us write first u here, du is equal to TdS minus PdV plus sigma I is equal to 1 to R del u del n I dn I, okay, where S V, this is S and V, and n j, j not is equal to I. Similar for H also we got dH is the same thing which we got is TdS plus VdP, same thing TdS plus VdP plus sigma, this is the same thing, sigma del H del n I S P and n j, j not is equal to I dni. All right. And for Helmholtz function df is the basic, first two terms are the same for the single component, df is the property relation minus s dt, well, minus p dv plus the sigma del f del n I, well, dn I, and this t, v and n j, j not is equal to I, so I is equal to 1 to R. Similarly, if I write this dg, that means the Gibbs function which I have derived at the last, that this becomes equal to, oh, before that we have to write this, we have not finished this dg, this is not the final equation, I am sorry, because we have to again write in the same fashion, that if I now make the differential g from this, so this we have learned earlier, again I am doing TdS minus S dt, and dH is du plus PdV plus VdP, du plus PdV plus VdP, so it was done earlier. So du plus PdV and TdS they cancels, so dg is VdP minus S dt. That means you see that S becomes equal to this, that means del g del t at constant p and n. That means if g could have been expressed in terms of p and t, so dg becomes this into dp, this into dt. That means this is del g del t, that means in place of del g del t we put minus s, and in place of del g del p we put v. So that we are not separately putting it here, we straight we will put it here, that minus s dt, okay, plus v dp. That means in this equation I am putting, as usual I did s instead of this and v instead of this, plus this term sigma del g del n I, well, tp n j, j not is equal to I dn I, and this summation is from I. Now we see one thing, that these four equations, carefully you see that these first two parts similar to the single component systems, but this additional part is there for multi-component system comprising of this term, this comprising of R components. So these are the terms, and this is defined as the chemical potential. Now I define the chemical potential. First, this leads to the definition of chemical potential, and chemical potential is defined with for a particular constituents or a particular component. That means each component has got different chemical potential. So for chemical potential of ith component, mu I is defined as any one of these derivatives. That means it is defined either as del u del n I, that means this derivative I is equal to 1 to R S V n j, or by any one of these chemical potentials may be defined by this one del H, any one of these can be the definition of the chemical potential depending upon the cases. Nj, J naught is equal to I, J naught is equal to I, well, and equals to this one sigma, sorry, I am extremely sorry, this sigma is not there, it is only for a particular component, sorry, del F del Ni at T V N J, J naught is equal to I, or equals to any one of these del G del Ni at T P N J, J naught is equal to I. So, this gives you the definition of chemical potential of the ith component del U del. That means the definition of chemical potential, you see, now we can give a physical definition like this, just stating this mathematical statement that chemical potential can be defined either as rate of change of internal energy with respect to the number of moles of that component when entropy, volume and composition of the other components remain same, or it can be defined as the rate of change of enthalpy with respect to the number of moles of that particular component for which the chemical potential is defined when the entropy, pressure and the number of moles of other components are fixed. Similarly, it can be defined as the rate of change of Helmholtz function in with respect to the number of moles of the component for which the chemical potential is defined when temperature, volume and the number of moles of other components are fixed for the system, or the rate of change of Gibbs function with respect to the number of moles when temperature, pressure and the number of moles of other components are fixed. So, any one of these four can be defined, but usually, conventionally or usually this is defined as the chemical potential of a multi-component system del G del Ni. Now, one thing you see from all these four equations, the chemical potential is a indication of a change of certain energy quantity with respect to the number of moles when a constant is placed on the process, executed by the system, like when we consider U as that energy quantity, then SV constant, H then S and P constant, F then T and V constant, then G, T and P constant. For example, if we take this definition, then we can tell physically that chemical potential of a system is like this, that if there is a system of our components, well, and if we make the temperature and pressure constant and if we allow any process, this is possible because it is a multi-component system. Single component system, temperature, pressure fixed means the other properties are fixed, then the system is at a fixed state, that therefore there is no process takes place, but in a multi-component system this may happen, as we have already recognized earlier in case of reactive system, that reaction can take place at constant temperature and pressure. Their mass transfer process can take place at constant temperature or pressure. This can happen because of the material flow in and out, that means there may be a change in the number of moles. So, if we conceive that a system changes its state like this, a multi-component system where temperature and pressure remains constant, then the change in the Gibbs function, with respect to the change of the number of moles of a system, that means how the Gibbs function responds with the change in the number of moles. How sensitive is the change in the Gibbs function due to the change in the number of moles of a system, which can be caused by a mass transfer, addition or removal of the materials, or by chemical reaction, okay, is the index of the chemical potential of that particular constituent or component. If the chemical potential is high, that means for a small change in the number of moles, there is a large change in the Gibbs function, which is an index of the energy, Gibbs function. At constant temperature and pressure, the change in the Gibbs function gives a change in the energy quantity like that. If you remember, in case of availability, we have seen that if there is a single component system, even this system interacts with the surroundings and the temperature and pressure remains constant with that of the surrounding, then we recognize that the change in the Gibbs function gives the maximum work, useful work that we can get out of the system. So, this Gibbs energy is a concept of work potential. So, here also you see these are the energy potential, these are short of energy potential. So, this energy potential their derivative with respect to the number of moles. That means, how do they change with the change in the number of moles of a particular component with some constraints in the process executed by the system is physically the concept of a chemical potential, which can be defined in terms of internal energy, in terms of enthalpy, that means the change of internal energy with respect to the change in the number of moles, in terms of enthalpy, change in the enthalpy with the change in the number of moles, in terms of Helmholtz energy and in terms of Gibbs energy, as given by these equations we have written. That any of these equations can be the definitions of the chemical potential of the ith element. Usually this definition is used to symbolize or to express the chemical potential of an ith component. Now, if I use this nomenclature mu I, then I can replace all this by mu I, and I can write again this, well, I can write these equations again like this: du is equal to now Tds minus Pdv, well, plus sigma. Now, with this nomenclature, as we have defined mu I now, I can write mu I dn. Well, I is equal to 1 to r. Similarly, now I can write dh is Tds plus Vdp, well, plus sigma del h del n I, well, sorry, extremely sorry, because I am writing in terms of the mu I am sorry, mu I dni. So, these are the extra term. Now, we can write in short that we do not have to write all the differential terms, that minus sdt minus pdv plus again this mu I dni. But in all equations, one thing, that the definitions of this mu I are different, that they are expressed as a different quantities. So, dg is equal to minus sdt plus vdp. So, in terms of the chemical potential, now I can write mu I dni, I is equal to 1 to r. So, therefore, I can write these equations now in terms of, so therefore, we see that in a multi-component system, the additional terms apart from these two which we have already recognized, we recognized earlier in a single component system, additional third term is like that. So, as a whole, this is the third term. There are number of terms because this is a summation side. That means the additional term is the sum of this mu I dni. That means the chemical potential into multiplied with the change in the number of moles. Chemical potential of the element into number of moles, change in the number of moles of that component, not element, sorry, component. So, these are the extra terms added, and this is the concept of chemical potential. All right. Now, I will write one other relations. So, this is a routine that from these expressions, if we see, we can have several other relations. Now, several other thermodynamic property relations. For example, if we consider this one first. So, this is an exact differential equation. So, we can use these exact differential equations thing, and we can develop certain other relationship. For example, if we use this, then we can write del mu I am writing first, you can understand, del t at constant p and n is equal to minus del s. So, we can generate a number of such which are very important, number of such nj, j naught is equal to I, chemical thermodynamic relations. How do you derive it? Del mu I del t at p and n, constant n, del mu I del t will be what? That will be equal to del s, that means del s del n I, okay, at constant t and p and other nj. Just a cross differential, as you know, that is the properties of the exact differentials, that if dg is the exact differential, so if you differentiate this with respect to another variable, will be equal to the differential of this with respect to this variable, that we have already recognized earlier in derive other property relation. Similarly, we can write del mu I del p, that means I differentiate with respect to del mu I del p and constant t and n, constant t and n, del mu I del p, that means it will be equal to del v del ni, okay, del v del ni, and that will be equal to t and del v del ni, t and p and except Ni, that means Nj, J not is equal to I. Okay. Similarly, we can get this type of relationship from exact differentials for each of these, given their number of terms. That means I can write del mu k, del mu I, for example, I and k, denoting I and k as the two components, two general components. There will be differentiation of the chemical potential of the ith component with respect to the number of moles of the kth component at all these T, P and Nj, J naught is equal to k, equals to del mu k del n I, okay, T, P and Nj, J naught is equal to I. That means these are the relationships which are being found, thermodynamic relations, by exploiting the property of the exact differentials of G. G is an exact differentials. That means the coefficients of this differential quantity dt, dp, the coefficient, they are being differentiated, cross differentiated partially and can be equated like this. So this comes from this. Similarly, we can write equations from similar property relations we can derive from this equation dH and du. I just write the relationship which we can derive from this equation, that you can see afterwards in your hall or room, that using this equation, the exact differential properties, I can write. That means if you differentiate mu I with respect to t at constant v and n, will be equal to the differentiation of s with respect to ni at constant t, v and other n's. Like that we can write the relationship which I write now, that will be del mu I del t, well, v and n is minus del s del n I T, V and N j, j naught is equal to I. Well, similarly del mu I del V at constant t and n is equal to minus del p del n I at t, v, n j, j naught is equal to I. And amongst all the moles, then del mu I del n k, well, T, V, N, J, J naught is equal to K is equal to del mu K del N I, and T, V will remain same, and here N, J, J naught is equal to I. So like this we can derive three sets of relationship for this and this from these two equations also. Now I will come to a different thing, another thermodynamic important relations for multi-component systems, for which I like to state one theorem known as Euler's theorem. Euler's theorem, one theorem known as Euler's theorem on homogeneous function. Euler, there are various Euler's theorem. It is a particular mathematical theorem on homogeneous function. Euler's theorem on homogeneous function. What is that? If a function f of number of independent variables, let z1 to zr are independent variables, they are the independent variables, a function of z1, z2, zr. If this function is homogeneous in z, homogeneous of order m in z, that means these equations are such, they are the homogeneous, these functions are such, they are homogeneous of order m in z. Then the Euler's theorem tells, first of all let us see that what is meant by homogeneous of order m in z. Just recapitulate the basic mathematics, which means that if all the z variables, that z1, z2 are multiplied by m, or multiplied by, sorry, not m, multiplied by a multiplier, then the function will be multiplied by the m index of the multiplier. You understand? If it is homogeneous of order 1, then it is multiplied by a constant multiplier, the function will be multiplied by the constant multiplier. Just for an example, if it is a homogeneous in m, then f of, if I make a constant multiplier lambda z2, that means in the function all the variables are multiplied by the lambda, then this function will be equal to lambda to the power m, which will come as a common, so that it can be again expressed as the same function z1, z2, z1. It means that this is the definition that the function f is homogeneous in M. This is the basic recapitulation or the recapitulation of the basic mathematics, that a function of multivariable multiple variables, so that a homogeneous of order m means that all the independent variables, if they are multiplied by some constant lambda, then the function becomes that lambda to the power m. This is the definition of the homogeneity. If it is homogeneous of order 1, that means lambda into this. Now, if a function is homogeneous of order m in all the z's, then Euler's theorem is like this: m into f, that means this function, is sigma del f del z I, that means in any one, into z I1 to R. So this is the Euler's theorem. Well, this is the Euler's theorem. This is the Euler's theorem, that m into f is del f del z I into z I1 to R. I will exploit this Euler's theorem to define or to derive very important thermodynamic relation. Now, you see again at the beginning we told that u as a function of S, V and n1, n2 to nr, and we have seen finally that this u is a homogeneous function of order 1 in S, V and n, that we have already seen. Okay. So this is the equation. If you see this differential equation here, you will find out that u is a homogeneous function. U is a homogeneous function of order m. Homogeneous function of order 1 in S, V and n's, all n's. So if now I exploit this thing, this information with the use of this Euler's theorem, we can write u is equal to, here m is equal to 1, then del f del, that means del u del s into s. Del u del s means v and n will be constant, s plus del u del v, then del u del v at s and n v plus sigma of del u del n I times n I. Well, obviously S, V and n j, j not is equal to I is equal to 1 to 1. That means this is the Euler's, we have used the Euler's theorem. That means u is equal to this, m is 1 in this case. So del u del s already I know this is t, though this is ts, and this already I know p, pv, and this is by definition is mu. That means already we have written that mu I ni. All right, sigma of mu I ni, I is equal to 1 to 1. Now if I take this in the left hand side, it becomes u plus pv minus ts is equal to sigma of mu I ni, I is equal to 1 to R. Well, now these things can be written as you know that u plus pv is h and h minus ts is, what is h minus ts? It is g. So therefore we can write g is equal to sigma mu I into ni. It is a very useful relationship. Now you see it is a very useful relationship. G is equal to I is equal to 1 to R mu I ni. All right. So this relationship we get a very important thing. That means for a multi-component system we see that the Gibbs function, for example, is the sum of the chemical potential times the number of moles. That means it is the molar weighted sum of the chemical potential. Now for a single component system, you see, for a single component, now you see from here we get one thing. For a single component system, one very interesting result comes. G becomes equal to, if you use this thing, it becomes is equal to mu into n, because there is no ni for 1 to R. So therefore mu is equal to G by n, which is small g. For a single component system, how do you define the molar property? That is property per unit mole. Mole is the mass, that is the unit of, that is the index of mass, that is the amount of the system, that is the amount of the system, mole is the amount of the system. Well, so therefore it is G by N, that is the molar Gibbs function. Molar, sorry, big G, molar Gibbs function. This is the molar Gibbs function. So therefore for a single component system, thermodynamic potential becomes equal to molar Gibbs function. It will be more clear afterwards when I will discuss the partial molar property. So therefore today I will end here that G is sigma mu I n I, and for a single component system, for this we get mu into it. That means for a multi-component system, the Gibbs function is the sum of the product of chemical potential and the number of moles. For a single component system it becomes this, that means the thermodynamic potential is the molar Gibbs function. Okay, fine. So next class I will discuss afterwards. Okay, so thank you for today.